Assalamualaikum warahmatullahi taala wabarakatuh and good day everyone. My name is Riduwan Zakaria and I will present a study entitled Effect of Barrel Temperature on Warpage and Cycle Time of Injection Molded High Density Polyethylene. This study was conducted together with my friend Muhammad Hazri Omar and Muhammad Adli Harun. Today's presentation we will be divided into four sections, starting with an introduction and conclusion in the last section. Uh, there, there will be other subsection for each section. In the introduction, there will be four subsection, and I will explain each of them in depth. Injection molding is important in manufacturing, producing various plastic components and product efficiently. It enables the mass production of intricate shape with high precision, proving indispensable in manufacturing. It achieves cost effectively through high volume production with rapid cycle, reducing manufacturing time and cost. Additionally, it ensures consistent quality across large batches. Injection molding entails injecting molten plastic into a mold cavity to shape it upon solidification. This precise process involves managing parameters like temperatures, pressures, injection speed, and clamping force meticulously. Controlled parameters guarantee the production of consistent, reliable, and high quality product. Temperature is crucial in injection molding as it affects the behavior of molten plastic. Precisely controlling a barrel temperature is essential in this intricate process. Variation or improper control can result in defect like warpage, sigma, and burn mark in molded component. Precisely controlling barrel temperature is crucial for melting and homogenizing plastic material, impacting the entire molding process and part properties. Manufacturers prioritizing this control unlock the potential for consistently producing high quality, defect-free plastic component efficiently. In the manufacturing landscape, mastering barrel temperature is essential for excellence in injection molding where precision is paramount. Now, let us observe the problems associated with the injection molding process. First, careful control of barrel temperature is needed to ensure effective melting and homogenization of plastic materials, impacting the entire molding process. Observing changes in warpage and cycle time in response to variation in barrel temperature is essential. This practice unlocks the potential for consistently producing high quality, defect-free plastic components efficiently and cost effectively. Based on the author's knowledge, the previous study did not extensively examine the impact of the barrel temperature on the warpage and cycle time of molded part, particularly when applying autodesmol flow. Thus, the objective of this study is to analyze the influence of barrel temperature on the warpage and cycle time of the injection molded high density polyethylene or HDPE using the Autodesk Mold Flow software. Next, we shall move to the methodology section. On a figure 1 shows a plate part with a feed system that used in this study. The dimensions are tabulated in table 1, whereby the length is 100 86.5 millimeters. The thickness of part is 4 millimeters and the width is 20 millimeters. Table 2 presents an overview of the default properties of HDPE sourced from the Autodesk Morphlow software library. Then a comparative assessment of deflection and cycle time across various melt temperature is conducted to ascertain the interrelationship among them. This evaluation entails the computation of a relative value denote, denoted as an element of which is expressed by equation 1. Here, AI denote the specific value corresponding to each melt temperature, while A def represents the deflection and cycle time value at the minimum melt temperature of 210 degrees Celsius. Selecting the lowest melt temperature as the baseline is justified by expecting it to yield the minimum deflection and cycle time values. Finally, a simplified depiction of the process is achieving the objective of the study is illustrated in figure 2. Start with create a 3D model and lastly discussion process. The subsequent section will delve into the result and discussion. Here I will elaborate on the findings concerning each of the response studied, especially focusing on warpage and cycle time, providing a detailed analysis of their outcome. Figure 3 and 4 illustrate the product deflection result obtained from Autodesk Morphlow. Specifically, this figure depicts the deflection at a melt temperature of 270 degrees Celsius for a mold temperature of 40 degrees Celsius and 53 degrees Celsius, respectively. In both figure, the region with the highest deflection is observed in both ends, which is indicated in the red area, while the middle part, which is indicated in the blue area, exhibits the lowest deflection. Additionally, it is noteworthy that the deflection is notably higher at a mold temperature of 53 degrees Celsius compared to 40 degrees Celsius. Next, figure 5 shows the deflection profile across various melt temperatures from 210 degrees Celsius to 270 degrees Celsius. It compares two different mold temperatures, a blue line for 40 degrees Celsius and a red line for 53 degrees Celsius. The result indicate that deflection increases linearly with higher melt temperature for both mold temperatures. At 40 degrees Celsius mold temperature, deflection remained consistently lower across all tested melt temperatures compared to 53 degrees Celsius. To better understand how changes in melt temperature affect the deflection of molded product, we use relative amplification as a key metric for analysis. Figure 4 displays the relative amplification values across all tested melt temperature level. The red bars represent a mold temperature of 53 degrees Celsius, while the blue bars represent 40 degrees Celsius. The figures shows that as melt temperature increases, relatively amplification also rise for both mole temperature setting. However, throughout the entire range of melt temperature, the amplification values consistently favor the 40 degrees Celsius for uh, the amplification values consistently favor the 40 degrees Celsius mole temperature over the 53 degrees Celsius mole temperature. The highest amplification, in nearly 3%, occurs at melt temperature of 270 degrees Celsius, while the most significant difference between the two mole temperature setting is observed at 230 degrees Celsius melt temperature. These findings highlight the complex interplay between melt temperature and mole temperature, providing insight into the factors influencing part deflection in injection molding process. Figure 7 illustrates the example of the responses obtained from autodesmo flow. The cycle time, which encompasses all phase of the injection molding process, consists of fill time, packing time, cooling time, and mold open time. Throughout the entirety of the simulations, both packing and mold open time remain constant at 10 seconds and 5 seconds respectively. However, variation are solely observed in fill and cooling times, which considerably influence the overall cycle time. Figure 8 depict the simulated result for different mole temperature values. As melt temperatures increases, fill time decreases in both scenarios. Conversely, cooling time increases with higher melt temperatures, consistently exceeding fill time. A mole temperature at a mole temperature of 53 degrees Celsius requires a longer cycle time compared to 40 degrees Celsius, mainly due to the extended cooling period. Then, as the melt temperature rises, the relative cycle time increases for both mole temperature setting. The values for a mole temperature of 40 degrees Celsius are almost identical to those at 53 degrees Celsius. Additionally, the highest relative value, nearly reaching 20%, occurs at melt temperature of 270 degrees Celsius. It is important to highlight that compared to the relative deflection value, cycle time exhibit the most significant sensitivity to variation in melt temperature. In conclusion, the current study has shown that first, there's a direct correlation between the melt temperature and both deflection and cycle time, showing a linear increase with higher melt temperatures. Second, the highest relative value, approximately 20% for cycle time, is observed at the maximum melt temperature of 270 degrees Celsius. In contrast, the impact of deflection is relatively modest with a relative value of around 3%. Third, the findings highlight the importance of considering variation in melt temperature during the injection molding process, both during development stage and in practical application. That's all for now. I appreciate your time and consideration. I'm pleased to answer any inquiries you may have at this time. Thank you, everyone.